Okay. Last time we studied the Lagrangian density and earlier Lagrange equations for the equation of motion of the electromagnetic field. We defined the Lagrangian density for the electromagnetic field and the sources. Now, today we will look at the case what happened if we define the Hamiltonian density and what we can learn from that Hamiltonian density. So basically we will derive the conservation laws. So energy and momentum conservation laws we will derive. So if you think about the Hamiltonian of a system, so that is Pi canonical momentum, Qi dot minus L. Qi are the coordinates, Pi are the canonical momentums. So this is valid for I particle. So canonical momentum is del L over del Qi dot. So doing an analogy with the Lagrangian density, we can define that the Hamiltonian density, and the coordinates in that case are the fields and the derivatives of the fields with respect to the time. So the Hamiltonian could be written as a volume integral of Hamiltonian density. So let us define a Hamiltonian density, or let us say in that form. So H curly is the Hamiltonian density and the volume integral of this is the Hamiltonian. So the coordinates are the fields and derivatives of the fields, which are corresponding to velocities, and that could be more than one field, more than one field at any location of space-time. So K could be 1, 2, 3 and so on. So the analogy with the Hamiltonian and the Hamiltonian density could be the following. So suppose that this is the Hamiltonian, and instead of particles we have fields for a given space and time. So, and instead of Lagrangian, we have the Lagrangian density. So derivatives with respect to the derivative of the field with respect to the time. So later we will generalize this to the different coordinates. So at this moment we are taking the derivative of the field with respect to the time alone. So then this corresponds to Pi, and for Qi dot we can write del Vk over del t and minus the Lagrangian density. So this is the Hamiltonian density. So let us look at the analogy between them. So derivative of Lagrangian with respect to the Qi dot is replaced by the derivative of the Lagrangian density with respect to the derivative of the field with respect to the time. And Qi dot is the del phi over del t. And at a given location, you can have more than fields, one fields. So field variables the fields and the derivatives in general, but in that presentation I take the only zero component, that is del over del t. So this is one-to-one analogy with the Hamiltonian and Hamiltonian density. So this is a scalar at this point, so that is nothing but the scalar quantity, so one term. You can define that the stress tensor, which is called a canonical stress tensor. So all you do, instead of taking the derivative with respect to the time, you can take the derivatives with respect to all coordinates. So del over del 0, del over del 1, del over del 2, del over del 3. So the definition of the canonical stress tensor is derived from the Hamiltonian, and that is, the definition is the following. For a second rank tensor, T alpha beta, you can write the Hamiltonian, but you can use that instead of derivative with respect to time, you can write the derivative with respect to all coordinates, and for a given space and time you can have more than one fields, and the situation will be the following: del Lagrangian density over del alpha phi k, del beta phi k, Lagrangian density multiplied with the metric tensor. So alpha is upstairs, beta is upstairs, phi is the field variable, and del of alpha or del of beta are the derivatives of the field variables. The difference between this and that, this is a 0th rank and this is the second rank tensor, and we will see that each element has the different physical meanings. Now let us think about let us try to evaluate this canonical stress tensor. So this is generalization of the Hamiltonian. Instead of taking the derivative with respect to the time, we are taking all possible pairs of the derivatives, so of the fields with respect to time coordinate and the space coordinates. So if you plug to Lagrangian density of the electromagnetic field, which we defined last time, 1 over 16 pi f mu nu f mu nu. There's the interaction term, but let us work on with the free Lagrangian density without interacting sources. So the source term was related with current density, scalar product of the current density with for potential. So let us ignore at this point. So what are the elements of this Lagrangian density? F mu nu are related with the derivatives of the four potentials. Then nu mu a nu del nu a mu. So now we have a field that is the four potential, and the derivatives of the fields are nothing but del mu a mu and so on. So the Lagrangian density is constructed by derivatives of the four potentials. So if you want to calculate that the canonical stress tensor, first we have to evaluate the, now let us, instead of Lagrangian density, let us say that the Lagrangian density of the electromagnetic field. So that quantity, derivative of the Lagrangian density with respect to the derivatives of the four potential, let us call del alpha a lambda. And if you take this derivative, which we had done last week, you will obtain the following. So minus 1 over 4 pi, you have to go and to get your lecture notes and try to derive yourself what we have done last time. This index actually is the upstairs, del alpha, and this index is in the downstairs. So upstairs index contravariant is alpha, and downstairs index lambda is down. And so this piece we needed, and instead of that we have the derivative of the four potential. So then we can write that the canonical stress tensor in the following form: T alpha beta. We have only one field, that is the four potential, no summation needed, and that will be what? This piece is there, that is minus 1 over 4 pi f alpha lambda del beta, and for potential del, so this is nothing but the derivative of the four potential, del beta a lambda, and minus the metric tensor acting multiplied with the Lagrangian density of the electromagnetic field. So what are the free indices? Alpha and beta. Lambda and lambda is contracted, and here the free indices are alpha beta. So you can arrange the indices. You can make this as a downstairs indices using the metric tensor. 1 over minus 4 pi g lambda mu f mu lambda del beta a lambda g lambda beta Lagrangian density of the electromagnetic field. Is it okay? Yes. If you contract mu and mu, this will be the alpha, and lambda is contracted. So mu and mu, lambda contracted, and the free indices are alpha beta and alpha beta. So if you calculate the values are the following. First of all, the Lagrangian density of the electromagnetic field is E square minus B square over 8 pi. So that is a Lorentz scalar invariant everywhere, doesn't change. And the elements of the canonical stress tensor are the following. 0, 0 is 1 over 8 pi E square plus B square plus 1 over 4 pi divergence of phi E. So 0, 0 component of the canonical stress tensor. As you see that is the first term is the total energy density, E square and B square. Lagrangian density is E square minus B square, and you have an additional term that is the divergence of a potential times the field, and if you take the volume integral of this, this goes to surface integral, and you can estimate the T00 is a total energy of the electromagnetic field. So let us look at the other components. 0I is 1 over 4 pi E cross B I component plus 1 over 4 pi divergence of E component of the vector potential times the electric field. And 0I is related with what? E cross B is related pointing vector, or more generally is related with the momentum of the field. And this term is the divergence of a field. If you convert to the volume integral, this goes from the divergence theorem, and this could be expressed as a total momentum of the field. So this is related with the momentum density of the field. So, and if you look at the I0, that is 1 over 4 pi E cross Bi 1 over 4 pi curl of scalar times the vector potentials of the I component, and del over del Ct scalar potential times the I component of the electric field. So as you see that it is containing lots of things here. So it is not a symmetric tensor. 0I is not equal to I0. It is depending on the scalar and vector potentials, therefore they are gauge dependent. So basically, if you calculate the volume integrals of the 0,0 component and 0I component, you can obtain physical quantities. 0,0 integrated through the volume will be what? 1 over 8 pi E square plus B square, E square plus B square times G cube X, and plus 1 over 4 pi divergence of scalar potential times the electric field. From the divergence, this is a volume integral, this goes to the surface integral. So, and when the surface is large, and this all vanishes and that is 0, it has no contribution. So basically, the volume integral of T00 of the canonical stress tensor is nothing but the energy of the field. Total energy of the field. 0I so if you integrate the 0I, again you have the total divergence through the volume integral. This doesn't contribute, and this is E cross B, and that is equal to, in Gaussian, is C times the momentum of the field. So we have the nice results if we integrate through the volume of 0, 0 and 0I, but I0 is very complicated, so it doesn't say even we integrate through the volume. But as you see that this elements of this tensor gauge dependence, that depends on the potentials. It is not symmetric, and the one other important thing, trace of this tensor is not 0. So basically this is the situation at the moment. So how about the divergence of this tensor? So let us look at the divergence of this tensor. Can we obtain some conservation rules from the divergence? So basically, T alpha beta, take the divergence of respect to the alpha and use the full definition. So this is the canonical stress tensor. Let us look at the divergence of this. So you can have in general more than one field at a given space and time. Del alpha of this whole term and the other term. So in general, so apply this for any Lagrangian density, not the electromagnetic field. So that will be del Lagrangian density over del alpha phi k, del beta of phi k minus del alpha g alpha beta Lagrangian density. So we take the divergence of the in 4 dimension of the canonical stress tensor. So the first term and the second term is taken. This is alpha, and alpha is contracted, and it is nothing but del beta Lagrangian density. Is it okay? Beta is free index, alpha is contracted, and beta is the free index. So let us apply the derivative to the two terms, one term here, the other term here. So summation through all possible fields, del alpha of del Lagrangian density with respect to the derivatives of the fields times del beta phi k, this is the first derivative, plus del Lagrangian density over del phi k. So this is now free, del Lagrangian over del alpha phi k, and the derivative is acting del alpha del beta Lagrangian density, and the final term is del beta Lagrangian density. So, and what is this? So if you remember that the earlier Lagrange equations, this is the one term of the earlier Lagrange equations. So remember the earlier Lagrange equations, that is del beta of del Lagrangian density del beta phi k minus del Lagrangian density over del phi k is equal to 0. Or you can write this as a alpha and alpha. So basically this term is nothing but the, from the earlier Lagrange equations, that is nothing but the del Lagrangian density over del phi k, and next to it multiplied by del beta of phi k, and plus derivative of the Lagrangian density with respect to the derivatives of the fields and you have del alpha, del beta, you can switch the order and you can write this as a del beta del alpha of Vk minus del beta of Lagrangian density. So I did nothing. I used the first derivative to the earlier Lagrange equations, and this whole bunch is replaced by del L over del Vk. So now you have the del beta Vk, and the next del Lagrangian density over derivative of the fields times del beta del alpha Vk, and so on. What are the free indexes? Beta. So what are the free indexes? Del alpha T alpha beta. So this is contracted, beta is free index, beta is free index, and this is contracted, beta is a free index, and so on. So this is the divergence of the canonical stress tensor. So consider any Lagrangian which depends on the fields and the derivatives of the fields. Consider any Lagrangian which depends on the fields and the derivative of the fields. And if you take the derivative of this Lagrangian density, implies the following. So that is equal to del Lagrangian density with respect to the del Vk and del beta over Vk plus, so this is the derivative of the Lagrangian with respect to the Vk, and then you can take the derivative with respect to the second component, that will be plus del Lagrangian density over del of del alpha Vk. This is the derivatives of the fields, and the interior derivative will be del beta of del alpha Vk. So in general, if you have any Lagrangian density which is depending on Vk and the derivatives of the Vk, if you take the derivative of this Lagrangian density, that is very simple. You have to take the derivative of the Lagrangian density with respect to the fields, and this is multiplied with the derivative of the fields, and then Lagrangian density, take the derivatives of the Lagrangian density with respect to the derivative of the fields, and take the derivatives of the interior, means that the del of beta of del alpha k Vk. So if you make an analogy between the, or if you compare this, not analogy, compare this with the above, what you are seeing that this is equal to what? This whole term is equal to what? This whole term is equal to above this. So basically this term is equal to that, and that is equal to del beta over Lagrangian density. Therefore this is nothing but del beta over Lagrangian density minus del beta over Lagrangian density, and that means that divergence of the canonical stress tensor is equal to 0. So del beta of Lagrangian density, this whole term here, minus del beta over Lagrangian density, this will be cancelled, and we find a very important result for the canonical stress tensor. So just take the definition of the canonical stress tensor and take the divergence of this and use the earlier Lagrange equations in the derivative. We obtain an equation in terms of the derivatives of the fields and the derivatives of the fields. And for any Lagrangian density which depends on the fields and the field derivatives, and if you take the derivative of those, this whole bunch is equal to 0. So this is important because this gives conservation laws, which we will see in a moment. So del alpha T alpha beta is equal to 0. So what does it tell us? So let us concentrate. What does it tell us? Do you have any question here? You have to go by yourself, do all steps by yourself. So this is not difficult. So you have to familiar to the indices, and you have to look at the free indices. So what does it tell us? This divergence of the canonical stress tensor is equal to 0. So take this equation. I know that that is equal to 0. Multiply the volume element of the space and integrate. Not 4 dimensions, just the volume. So, and this is equal to del 0 T0 beta d cube x and del I Ti beta d cube x. That should be equal to 0. So basically I take the 0 component and the rest is 1, 2, 3. So that is del over del x, del over del y, del over del z. So basically this is the divergence with respect to the x, y, z, and this is a volume integral that turns to be surface integral, and we can write dA ni TIB as a surface. When the surface goes to infinity, all the fields die, and this term has the contribution as 0. So this is the application of the divergence theorem. How about the first piece? So this is equivalent to, so that is equivalent to del over del t and del 0 T0 beta d cube x have to be equal to 0 because this goes from the divergence theorem. If you take the volume integral, everything depends on the time, then you don't have to write that the partial derivative of time. You can write the exact derivative. This is d over dt, because del over del 0, del over del 0, del 0 is nothing but del over del t, but if you take this volume integral, only derivative is the time derivative, then you can replace with the exact derivative. And if you open this for the 0 element, so that is T00 d cube x. And if you open this term for the x, y, z, and that should be d over dt T0I d cube x have to be equal to 0. So I know that this term is equal to 0. Now I have the del 0 T0 beta, and I take the derivative outside the integral. Then I wrote the 0, 0 and 0i elements, and I obtained this. And what is this? T00 d cube x is the energy of the field. How many independent equations here? 4. 1 is the 0, the 3 for the space. Therefore, each term have to be 0 independently. And that tells us that the change of the energy of the field in time have to be equal to 0. And this 0I integration through the volume, that is the momentum of the field. Therefore, that tells us that the d over dt p field have to be 0. Okay, so basically canonical stress tensor finds the conservation laws. There is no any interaction with the electromagnetic field with the charges, currents, and the elements of the canonical stress tensor is not symmetric. It has gauge dependence, and also the trace is not equal to 0. So if the trace is not equal to 0, we have the difficulty for the photon mass. So this photon is massless, no mass. Therefore, the trace have to be 0. T alpha alpha should be 0. Trace of the stress tensor have to be 0. So we have problems with this canonical stress tensor. So canonical stress tensor is not symmetric. I am not going to define, but there are for conservation of the angular momentum of the field, and in that case you will need a symmetric stress tensor, and trace is not equal to 0, and that is a problem because for the 0 mass photons requires that the trace of the stress tensor have to be 0. But if you leave these two difficulties, this tensor gauge dependence. So for different potentials, this tensor is changing. So then we have to develop a symmetric stress tensor and see that the conservation laws, the forms of the conservation laws. So basically, let me erase the elements of the canonical stress tensor. And this is the form. So canonical stress tensor, and okay, good. You know that the del beta A alpha could be written as minus F lambda beta plus del lambda A beta. You know this. You know this. This is very simple. That is del F lambda beta is equal to del lambda A beta minus del beta A lambda. Is this right? This okay, F beta lambda is equal to minus of F lambda beta. It goes there as minus and plus of that. Okay, just plug this information here. Then T alpha beta. Oh, another thing, our Lagrangian density is the Lagrangian density of the free electromagnetic field without interacting with the charges. 1 over 16 pi F mu nu F mu nu. So instead of Lagrangian density, say f mu nu, instead of del beta a lambda, say f lambda beta del lambda a beta, and our canonical stress tensor takes the following form. T alpha beta will be 1 over 4 pi g lambda mu f mu lambda f lambda beta. I will check the result in a moment, plus 1 over 4 g alpha beta f mu nu f mu nu minus 1 over 4 pi g lambda mu f mu lambda del lambda a beta. So I will check what I wrote here from there. So this term, first term, g lambda mu f mu nu f lambda beta with minus sign makes plus. This is the first term. This is the first term. And nearby we have f mu nu, and this is coming from here. F mu nu is the Lagrangian density, and we have the minus, therefore it is positive there, and that is 16 pi, therefore we have a 1 over 4 times 4 pi, 16 pi. The leftover term, where is the leftover term? F mu lambda, and del lambda a beta, this term, and how about the metric tensor? Alpha mu. So let us look at the indices, free indices. Mu and mu is contracted alpha, lambda is lambda contracted beta there, and mu nu is scalar, that is alpha beta, and how about this? Mu lambda, that is alpha beta. So this is, I think, in the healthy form. So g lambda mu, f mu lambda, del lambda a beta. Okay. Okay. So the next thing, if you look at here, you are seeing that this bunch is depending on the electric field and magnetic fields. They are gauge independent. If you change the gauge, obeying the rules, so if you change the vector potential and scalar potential, obeying the gauge transformations, E and B doesn't affect it. Therefore, all elements of this are gauge independent, and at the same time this term is symmetric, but we have the additional term here which depends on the gauges because we have the 4 potential. But I know that in general del alpha T alpha beta is 0. I show you if I take the divergence, and let me call this bunch of as a theta alpha beta, and then let me work on what is going on this term. G lambda mu f mu lambda del lambda a beta. So let me see what is going on here, because I know that this is 0 in general. So let me do, then we can give a break. What is going here? This piece. So let us work on this piece. This is equal to del alpha. If we contract the mu and mu, that is nothing but f alpha lambda, if you contract the mu and mu, del lambda A beta. And if you take the derivative, what we are going to obtain? The derivative of the first one, del alpha f alpha lambda times del lambda A beta. And this is the derivative of the first one. Derivative of the other one will be what? F lambda f alpha lambda del alpha del lambda A beta. Okay. So tell me, what is this? Do you remember this? What is this? What is this? This is the Maxwell's equations. Okay. So if you remember that, that is equal to what? If that is 4 pi over c j lambda, I think. And so J is the current density. Since we don't have a current density, we are working the Lagrangian density for the free fields. This will be 0. Okay, this is the Maxwell's equations with the source terms. And how about this one? So there is a general rule here. I will show you. This is a tensor antisymmetric. So antisymmetric means that if you change the indices, this becomes negative. Okay, if you change the indices. But this is a symmetric. If you change the indices, nothing change. So I change the indices, lambda alpha, I put minus sign, and I change indices lambda and alpha. That is minus. But at the same time, these are dummy indices. I can change the lambda as alpha, alpha as lambda also. Okay? And what is this? This is the antisymmetric property. So this is the multiplication of the antisymmetric tensor with the symmetric one. But in the other one, you can say they are dummy at the same time. Alpha goes to lambda, lambda goes to alpha, and alpha goes to lambda. That is alpha, lambda, alpha, lambda, A beta. So I change the indices. This is antisymmetric tensor, this is symmetric, and I have a minus sign. But here, instead of lambda, I put alpha. Instead of alpha, I put lambda. I can do this, they are dummy. And what we are saying that this is equal to that. But if this is equal to that, that should be 0 because this is positive, this is negative. The bottom line, if you multiply the symmetric and the antisymmetric tensor, that will be the 0. Okay, that is the general rule. So this means that this additive term here is equal to 0. This is 0, and that means that del alpha t alpha beta del alpha theta alpha beta is equal to 0, and basically del alpha theta alpha beta is equal to 0. And what are the elements of the theta alpha beta? I call this piece as a theta alpha beta. I will call this piece as a theta alpha beta. They are gauge invariant. It is symmetric because if you replace the alpha and beta, nothing will be changed. And the elements are the following. So, and at the same time, divergence of this theta alpha beta is equal to 0. That is giving some conservation laws. So we will see that the conservation laws quickly. So elements are the following. I am not going to write the theta alpha beta again. That is very important. That is the symmetric stress tensor. And the elements are the following. Theta 0, 0. Theta 0, 0 is equal to 1 over 8 pi e square plus b square. What is this? Theta 0, 0, e square plus b square. That is the energy density. No additional terms. Just but energy density. And theta 0 I is 1 over 4 pi e cross b I. That is related with the momentum of the field. And all ij terms, I1, 2, 3, J1, 2, 3, is equal to minus 1 over 4 pi AI, AJ, BI, BJ, minus 1 over 2 canonical delta IJ E square plus B square. So do you remember this term? Do you remember this term? From chapter 6, that is the Maxwell's stress tensor. Maxwell's stress tensor. So basically, symmetric stress tensor 4x4, rank 2, has the following elements. Theta alpha beta, 0, 0 is the energy density, and 0, 1, 0, 2, 0, 3 are related with the momentum density. It is a symmetric tensor, and all ij elements are the Maxwell energy stress tensor. We call this Tijm with minus, that is Maxwell energy stress tensor. So it's symmetric. Trace is 0, satisfy the zero mass condition of the photon, and gauge invariant. And this satisfy some conservation rules. So I will generalize this symmetric tensor to with the sources in the next R. But if you look at this, what is going on here, the divergence of alpha beta is equal to 0. We said that we derive. And what does it tell us? They are giving that the covariant form of the sum of the conservation laws. So for example, if you look at that alpha theta alpha 0, What is this? Alpha is 0, 1, 2, 3. Del of 0 is del over del t. Del over del 1 is x, y, z. So basically, if you take the derivative of that, so you will obtain 1 over c del u over del t plus divergence of s is the Poynting vector is equal to 0. So indeed you can do this. So this is derivative with respect to time, and this is the 0, 0. If you put it, that will be the energy density. And if you do for what? 1 is the x. 1, 0 is what? 1, 0 is the moment related with the momentum density of the x component. Momentum density is related with the what? Poynting vector. And the open form of this. And if you do the del over del alpha for alpha I, you will find that the rate of change of the momentum density, the I component of the rate of change of the momentum density is related with the Maxwell stress tensor, divergence of the Maxwell stress tensor. So these equations are covariant, means that every Lorentz frame, the form is the same, and the open form of this. We have no, at this point, sources. At this point, if there is no sources, because our Lagrangian density is free, no interaction with the currents, tells us the following. Maybe this is a differential form, but if you take the volume integral of this, the volume integral of the energy density is the energy. Change of the energy is equal to what? So volume integral of this, what? Poynting flux through the surface. Basically, if you choose a volume, so if the energy density is decreasing, energy is decreasing inside, then we can observe what? A flow of the Poynting flux, so intensity, so flux of the electromagnetic wave. So basically not that, that we can observe what? Poynting flux, so energy per second. We would expect, what is this? Integral of this, S dot n, S is energy per second per area, so integrate this, the energy rate. So we expect that the decrease in the energy at the surface. And this is equivalent to the following. If you take the volume integral of this, this is the what? Total momentum. So derivative of the momentum is the force that is equivalent to momentum flux integration through that surface. Momentum flux, so therefore if the momentum of the electromagnetic waves is changing in a volume, we expect a momentum flux at the surface of given region. So they are covariant in all Lorentz frames. The forms are the same, but no sources at the point. So what happens if there is a source for source? These forms will be modified. We write these modified forms in the chapter 6, but we will do it again. So let us give a 10 minutes break. Then let us see how we can write that the covariant forms of the conservation laws if there are sources. So let us give a break, then we can continue.